Hi everyone, and welcome back to the Drawing Board by TBPi. This week we're going to be looking at intermolecular forces and the different physical phenomena that occur because of those intermolecular forces. So there are three main types of forces we're going to be looking at. Here they're arranged from weakest to strongest, starting with London dispersion, followed by dipole-dipole, and finally hydrogen bonding, which is the strongest of those molecular forces. And as we go through and look at what these different types of forces are and why they occur, it'll become pretty clear why they are arranged this way from weakest to strongest. So starting with London dispersion forces, these forces are instantaneous dipole-induced dipole forces, which is a mouthful, but I think will make a little bit more sense if we explain it in terms of an example. So let's consider that we have some atom here. You've got your nucleus of the atom, where you've got neutral and positive charges, so we'll put a little plus here. And let's say that this molecule is going to bump into another atom of the same kind. Well, generally, negative charges will be attracted to positive charges. So because these molecules are close to each other, you may see some grouping of your electrons kind of pulling this molecule towards the positive charge in this molecule. Now that means something similar is going to happen here, because now you have a bunch of negative charge built up on this side of your atom. You're not going to see a lot of electron density on this side of this atom because it wants to be repelled by these electrons. So you see a similar grouping of electrons on the opposite side of this atom. So you get this kind of partial negative charge. So you can see how this is kind of an induced dipole. These molecules are forcing each other to have a partial negative charge pointing in this direction for both of them. So then once you have these induced dipoles, you can see how molecules would be able to interact with each other with these induced dipoles. And you can also see why this would be our weakest force, because before any interaction can happen, you need to create these induced dipoles. Now, what if you already have dipoles in place to cause these types of interactions? Well, then you have dipole-dipole interactions. So let's say we've got some molecule here, and it's already got a dipole pointing in this direction. There's a lot of potential here for interaction with other molecules that also have dipoles, whether that's repelling each other or attracting each other. But you can see why this would be a stronger interaction than the London dispersion forces, because you don't need to create these dipoles before anything can happen, because they're already there. Now, the final and strongest type of force we're going to look at is hydrogen bonding. This is actually a more specific type of dipole-dipole interaction, and it is specific to hydrogen. Now, don't let the name fool you. This is not a true type of bonding. And the best example that I can give for how this works is using water. We've got our lovely H2O here, and we know that it has a dipole that looks something like this. Now, water molecules really like to arrange themselves like this. I'm just going to draw this down here so you can see more clearly with your dipole pointing this direction. It really likes to put a hydrogen here so that it can arrange itself to be close to this dipole. And this makes sense because we know that hydrogen will tend to have a partial positive charge here, since your electron density is being drawn this way towards your oxygen. And this water likes to arrange itself like this all the time. You know, you'll have another hydrogen here, and it's part of this water molecule. And this process will continue throughout your sample of water that you're looking at. So now that you've seen hydrogen bonding and how it works, it definitely makes a lot of sense why London dispersion is the weakest, since you need to induce the dipole before you can have any kind of interaction. And obviously an induced dipole is going to be a lot weaker than a true dipole. Then of course we have our dipole-dipole interactions, where because the dipoles already exist just based on whatever molecule you're looking at. And then hydrogen bonding, which is a more specific but much stronger form of dipole-dipole interaction. So that's all fun, but why do we care? What do these forces do for us? Well, your intermolecular forces affect a lot of physical properties of your different compounds. So it'll affect things like your boiling and melting points, your vapor pressure, your surface tension, and your solubility. If we look at a few examples, it becomes pretty clear why this happens. So we can start by looking at boiling and melting points. How exactly do intermolecular forces affect those? Well, if you think about, let's say we have, a container of some liquid, full of our little molecules here. If those molecules really like to stick to each other in the liquid state, then you're gonna have a really hard time getting them to turn into a gas. So if you have really, really strong intermolecular forces in one phase, then that phase is really not going to want to switch into being another phase. So in this case, your boiling point would be really, really high because this material really wants to stay a liquid. Now, for melting, on the other hand, it's a similar idea. if we have some solid made up of all of our different molecules, if that solid is bound together by really strong intermolecular forces, you're going to have a really high melting point. And of course, the inverse for both of these is also true. If you have a liquid with really weak intermolecular forces, then it's going to have a really low boiling point because it'll be easier to get the molecules to let go of each other and release into your gas phase. Likewise, for your solid, if the intermolecular forces holding your solid together are not very strong, then you're going to be able to melt it pretty easily and at a relatively low temperature. So what about vapor pressure? What impact are intermolecular forces going to have on our vapor pressure? Now, a lot of people think of vapor pressure and boiling point as being the same, but they really aren't. What they have in common is that when your vapor pressure is the same as your ambient temperature, then your substance will boil. But that doesn't necessarily mean that that's the only time we care about vapor pressure. So if you consider again some container full of our liquid that contains whatever compound we're looking at, your vapor pressure is essentially how much of this substance is already in the air even before you're boiling. There's a concept called vapor-liquid equilibrium, which for the sake of this class basically means that when you have a cup of some liquid sitting out, that there will be some amount of that liquid in the air around the liquid, whether you're boiling or not. And that amount is measured using your vapor pressure. So you can kind of logic through this the same way that you logic through your different boiling points. The higher your vapor pressure, the more compound you have out in this gas phase that's in contact with your liquid. So if you have really, really strong intermolecular forces, then not very many of those molecules will be able to escape into the air. If you have really, really weak intermolecular forces, you're going to be able to release more of those molecules into the air and therefore have a higher vapor pressure. So logically, it's very similar to boiling point, but the physical relationship that you see because of those intermolecular forces is a little bit different when you're considering vapor pressure instead of boiling point. Now onto surface tension. I think the best way to think about surface tension is if you put a drop of water on a flat surface, that drop of water will tend to hold its little dome shape instead of spreading out in a really thin layer over the entire surface. And that's because water has a relatively high surface tension, but some substances like gasoline, for example, if you tried to put a single drop of it on a flat surface, that drop wouldn't stay in a nice dome shape like water does. It would try and spread out. So a way to think about the impact of intermolecular forces on surface tension is if we have our flat surface here and we've got a dome of liquid, the molecules that are right along this edge all have to be holding on to each other pretty tightly to be able to hold that shape. Meanwhile, a liquid that spreads out a little bit more, these molecules aren't holding on to each other quite as tightly. Another way to think about this is in terms of cohesive forces, which is that you have a liquid that really wants to stick to itself and hold this dome shape, or a liquid that doesn't necessarily want to hold on to each other quite as tightly, like gasoline or mercury is also the same way. So this one's a little bit easier to logic through. Obviously, the fact that these molecules are able to hold on to each other so tightly means that they have really strong intermolecular forces, whereas these guys, which are not holding on to each other quite as tightly, have much weaker intermolecular forces. Finally, we'll take a look at solubility and how intermolecular forces affect your ability to dissolve one compound into another. So I think the easiest way to think about this is think about the relationship between oil and water when you try and mix them in a cup. You're going to end up with this distinct layer between your water and your oil. The same thing can happen when you're trying to dissolve solids into a liquid. If you try and dissolve, let's say, some random non-polar solvent in water, it's not going to mix very well because water is a polar compound. It's the same reason that oil and water won't mix, because this is non-polar and this is polar. So an easy way to tell if you're going to be able to dissolve one substance into another is to look at the polarity of the two substances, and if they don't match, you're not going to be able to dissolve what you want to dissolve. If they do match, however, go right ahead. You'll be able to dissolve your solute into your solvent. Now, you might be thinking, wait a minute, if water can't dissolve oil, then how is it possible to hand wash your dishes? You know, if you've just eaten a plate of greasy food, you go to the sink, you wash it, the oil comes right off. How is that possible? Well, that actually comes down to the structure of soap specifically. So you can think of soap molecules as looking something like this. where you have this part here, which is nonpolar, and this end here, which is polar. This means that it can kind of bridge the gap between polar and nonpolar substances and allow you to use water to remove oil from a surface. So if we think about, let's say that plate of greasy food we were talking about, we've got our soap molecule here, again with the nonpolar and polar ends. If we have, say, a little blob of grease here, the molecules will arrange themselves with the nonpolar end facing the grease and kind of acting as a barrier between the grease and the water. But because these exposed ends here are polar, this allows our grease and our soap to interact with our water. So now that we've been able to create this outer layer here that water can interact with, the water can come in and sweep your grease away. And that has been an overview of intermolecular forces and their impact on the physical properties of various compounds.